In this video, I would like to work through several examples on how to determine a method's big O runtime complexity by just sort of examining that method's code. I have added various counters to all of the methods so that later on we can run the code and check our work. In this first example, not much is going on. We just have this single for loop that starts at 0, goes up to n, and I increases by 1 on each iteration. Therefore, this loop is going to run for a total of n iterations, and therefore the big O runtime complexity of the loop and of the entire method is O of n. In the second example, we now have two nested for loops, and the two loops do look essentially the same as the one in the previous question. They both start from 0, go up to n, and either I or j goes up by 1. So we know that the inner loop is going to run for n iterations, but then the inner loop this time is going to run for those n iterations on every iteration of the outer loop, and the outer loop runs for n iterations itself. So the total big O runtime complexity of this method is going to be O of n times n, or O of n squared. In the next example, we have sort of the similar setup with the two nested for loops. However, this time the inner loop starts at j equals to I. So what this means is that as in the outer loop I increases, the inner loop is going to start at a higher value of j and is not going to run for the full n iterations. So let's set up a table so that we can figure out the pattern that's going to be happening here, and we can figure out what this count would be when the method is done. So in the first column, I'm going to put the current value of I in the outer loop. And in the second column, I'm going to put the number of times that the inner loop is going to run for. So when I is 0, then j is initialized to 0 here, and this loop is going to run the full n iterations. As I increases to 1 on the next iteration of the outer loop, then the inner loop is going to start from j equals 1, and it's going to run one less iteration. So this is going to be n minus 1. Likewise, when I increases to 2, then we're going to shave off 2 iterations of the inner loop. So we go all the way up to n minus 1, which is the highest value of I you can have before this loop has to quit, because we want I to be less than n. And then when j is equals to n minus 1, then this loop is just going to run a single iteration before it has to quit. So when I is n minus 1, then the number of times the inner loop runs is going to be 1. So and then if we tally all of this up here, we see that this is just the sum of the numbers from 1 to n. And we do have a standard well-known formula for this, which is n times n plus 1 over 2. And then if we were to expand this, this is going to be n squared over 2 plus n over 2. And then in terms of big O, this is going to be O of n squared, because of course we don't care about the n, we drop the constants and so on and so forth. So the runtime of this method is also going to be O of n squared. So despite the fact that the inner loop runs fewer times than in the second example, both methods are still O of n squared. So what I would also like to do is, let's suppose that we give n equals to 100 to all of those methods. What would count be for that case? So in the first case, it's not very interesting. It's just going to be 100. In the second case, we would expect it to be n squared. So this is going to be 100 squared, which is 10,000. And then in this one, well, let's figure it out. Let's use the formula. So count is going to be 100 times 100 plus 1 all over 2. And if you crunch the numbers, this is going to be 5,050. So you can see the counts for example 2 and example 3 to be sort of in the same ballpark. Like 10,000, 5,000. Yes, this one is going to be smaller because we do run this loop fewer times. But they're still sort of in the same ballpark versus something dramatic like here, going from 100 for O of n to 10,000 for O of n squared. So definitely example 2 and example 3 are closer in terms of counts. Okay, in example 4, we have this single loop that starts from 0, and then we have this interesting terminating condition, and then we just go up by 1. So what we would like to figure out is how big can I be before this loop has to quit, which would tell us how many iterations it can run for. So we can rewrite this condition and essentially solve for I. So this is the same thing as I squared less than n. Or if you solve for I, this is the same thing as I is less than square root of n. So now we know how large can I get before this loop is going to have to quit. So this is going to be how many iterations this loop can run for. So therefore, the runtime complexity of this loop is going to be O of square root of n. And then if we compute the count here, and this is not going to be too difficult, this is just going to be square root of 100, which is 10. Okay, so in the next case, we still have the single for loop. We start from 1, we go up to n. However, the way we increase I looks rather interesting. We just keep adding I to itself each time. And this is really the same thing as just doubling I. So if I was to write in here something like this, this condition is actually equivalent to this one here. So if you put this in here, the loop would run the exact same way. So once again, we would like to figure out how many times can this loop run, so how large can I get? And it really becomes to be the question, well, how many times can we double I? And how many times can we double I before it reaches n is really this inequality here. And we can then once again solve for I, and this is going to be I less than log base 2 of n. So then the big O runtime of the method is O of log n, because we usually just drop the base when we do the big O. And what is count going to be? Well, let's try to estimate the log 2 of 100. And that is going to be 6 point something. And that's because if you do 2 to the 6, that is 64. That is the largest power of 2 that goes into 100. Because the next one, 2 to the 7, is 128. And that is already over 100. So the question is, well, are we going to round the 6 up or down? Are we going to take the floor or the ceiling of this log? Well, the answer is that our first iteration really starts at 2 to the 0. So then all the 6 exponents are going to come after 2 to the 0. We can run the first iteration and we can still double it 6 times before we have to quit. So really we should take the ceiling here. So this is going to be 7. And we can write out those 7 values of I. They're going to be 2 to the 0 through 2 to the 6, which are 1, 2, 4, 8, 16, 32, and 64. So those are going to be the 7 values of I for which this loop is going to run for. In the next example, what we have is really the reverse of what we had in this example. So I purposely put them side by side because now here we are starting from a very large I and we are cutting it down by 3 on each iteration, and we go on until we hit 0. So this here is going to be O of log, and now we are using base 3 because we are cutting everything by 3. And in the argument, we're going to put n cubed because that's where we start from right here. So then if we simplify things, we can use the power rule to bring the 3 in this exponent down. And then we can just drop the constant and the base. So this is also going to be O of log n. So you can really see how the two methods are really sort of reciprocal of each other. Really this here, multiplication by 2, is reciprocal of this division by 3 on each iteration of the loop. And by the way, you do really want to have this loop start from 1, because if you don't, then you're just going to be adding 0 to itself each time in here, and you're just going to have an infinite loop that's never going to exit. So that's why we started the other ones from 0, and that was fine. This here, you really want to start it from 1. Okay, in terms of count on example 6, so here is going to be the ceiling of log base 3 of 100 to the power of 3, and I just computed this. This is going to be 13. So it's not really a calculation that's easy to sort of figure out precisely just in your head, like we were able to do it in the previous example. But just what it is 13, just so that we know. In the next example, so we have a single for loop from 0 up to n. In this case, we increment I by 5 each time. So to figure out how many times can we do this, this is really going to be O of n over 5. So we would have to take whatever n is and divide it by 5 to figure out how many times, if we start I from 0, how many times can we increase it by 5 before we hit n. So then, of course, we drop the constants, so this is O of n. So it doesn't matter if it was something like I++, where we just increase I by 1, or we increase I by whatever constant. The runtime is still going to be linear, as long as we're not like halving or doubling it or whatever. It's going to be linear runtime right here. So to figure out the count, just going to be 100 over 5, which is 20. So you can sort of see, like, if, for example, if n was something like 20, then this loop would run for iterations with I 0, 5, 10, and 15. And that is really your 20 divided by 5 gives you the 4 iterations that we have here. And you can see the pattern of how when we kept on adding things to I, that turns into division when we do big O. And when we keep multiplying, when we keep on multiplying I, or we keep halving it, that turns into exponents. So it's sort of like addition really turns into multiplication when you do it enough times, and when you do multiplication enough times, that really turns into exponents. That's sort of the intuition of how this works here. Okay, for example 8, so we have quite a bit of things going on here. So let's take a look at this while loop. So we initialize I to be n. So as far as we're concerned, we're just working with n here. I just wanted to save n into I so that we can reuse n down in the next loop. So as far as this loop is concerned, we're going to be cutting I by 4 each time. So once we cut it all the way down to 0, then we're going to exit the while loop. So in this case, in this first loop, this is going to be just O of log base 4 of n, because of course the base 4 comes from us cutting everything down by 4. And then to figure out the runtime of the second loop, well, we see that we are going up to n times m. So we have to know what m is. Well, m was incremented on each iteration of this loop. And we know that this loop ran log base 4 of n times. So we know that that's what m is going to be. And m was initialized to 0. So it started from 0 and went up by 1 log base 4 of n times. So in this case, we're going to have O of n times m. And that is really just O of n log 4 of n. And that is, once we drop the base, O n log n. And this, of course, once you drop the base, is just log of n. So then, to figure out the runtime of the entire method, you have to take the slowest one of the two, because that's the slowest one is what's going to keep your method from leaving. So you take the slowest, and the slowest in this case is going to be O of n log n. So then to get the count, we want to compute this product of n times m, really. And this here, well, we know n is 100. And we know m is just going to be the ceiling of this log. So this is how we did the previous analysis with the log, where when we took the ceiling. And then in terms of powers of 4, if you do 4 to the 3, that is 64, and that's the highest power of 4 that can go into 100 without going over 100. So then this here is going to be 100 times the ceiling of 4 sorry, not 4. The power here was 3. 3 point something. So once you round that up, it's going to be 100 times 4. So that's going to be 400. So that's what the count is in this case. And the runtime is O of n log n. Okay, for the last example, so we have some of the nested for loops. So the outer loop is going to run up until n squared, and it just goes up linearly by 1. And then we have the two inner loops. So let's figure out what's going on with the inner loops first. So this one here, we have already done this type of analysis. So it's going to be j cubed is less than n. So we want j to be then less than cube root of n. So this one here is going to be O of cube root of n. And then the second one here, so this is this doubling condition. So we done this type of analysis, and we know that this here is O of log base 2 of n, which is O of log n. So then, out of the two inner loops, we want to figure out which one of them is the slowest. And the slowest is the cube root. So once again, we take slowest, and that is O of the cube root of n. And then we still have the outer loop running in O of n squared. So the total here is going to be the product of the slowest inner loop and the outer loop. So this is going to be the product of cube root of n multiplied by n squared. And if you add the exponents, this is going to be O of n to the power of 2 and a third. So that's the runtime of the entire example 9 here. And then we just want to figure out the counts. So in the first case, count 1. Well, in whatever, let's first of all figure out what the count would be if we were just running the inner loop. So that would be cube root of 100. And we would also take the ceiling of that because we do start from 0, so we have that extra iteration in there. And we want to multiply all of that by this n squared coming from the outer loop. So that would be 100 squared. So this here turns out to be 5. And then we end up getting that this here is going to be 50,000 for 5 times 10,000. And then as far as count 2 is concerned, well, here we're going to take the ceiling of log base 2 of 100 and times the same 100 squared. And we have figured out that this was 7 in the previous question, so this is going to be 70,000. And right now, the second loop is running slower than the first loop. And it just so happens that really the big O of the cube root of n and of log n, they're quite close. If you do shoot n up a little bit, you will see that this loop is going to slow down and this one is going to run higher. And we'll see this in a second here. But anyways, that's what the counts are in this current scenario. So here in VS Code, I do have all of the examples. And I run them from main, and I run them with n to be 100. And I'm sure to reset the count prior to running each example. So let's compile and run things. And we do see that we get the numbers that we computed by hand. So like the 50 and the 70,000 from the last example, and the 400 from the example prior to that, and then the 20, and the 13, and the 7, and so on and so forth. Okay, so what I would like to do next is I would just like to see if I can get this loop to become slower than this loop, as it should. So you have to up the count to 2000 to do that. So let's recompile and run. And we see that this now is 52 million versus 44 million. So this loop did become slower. Something else that's weird that happened here is the count, for example, 6 is 0, and that clearly doesn't make sense. And that's because this n cube here is so large that it caused an integer overflow. Like if we print it out, we see that this number is some garbage negative number. So the way you fix it is you just change this to a long integer. You give the integer more memory. So you make an integer into 8 bytes instead of 4 bytes. So now we see that the number, for example, 6 does make sense, and the 2000 cubed is also printed properly, and everything is okay. So this is just sort of a way how you can run those examples and test them out to check your work if you wanted to. And I purposely picked the examples here to sort of illustrate all possible ways that you can mess with the conditions and the loops to get different big O runtimes. Okay, thank you.